Hello, I am Madan Kumar, uh, Assistant Professor, Department of Aeronautical Engineering. So, in previous session, we discussed about the basics of potential flow theory, and in today's session, we are going to discuss about the potential flow equations and elementary flow models. You know very well about the potential flow theory. Now, we are going to see about the velocity potential equations. We know what is meant by potential flow. So, it is nothing but flow is inviscid and irrotational, and it is steady. And with respect to this, we have the Bernoulli's equation that is also valid everywhere, but it is not valid between 2 points on the streamline. The Bernoulli's equation is valid not on a single streamline, but from other streamlines, Bernoulli's equations are valid. And then we can define the flow potential and the stream function as the stream velocity, that is velocity potential function as gradient of x gradient as u velocity, y gradient as v velocity, and z gradient as w velocity. That is, velocity is varying with respect to x, y, and z is u, v, w. So, in this, the gradient of potential function, with respect to x, y, and z has been varying, and similarly, here the stream function is varying based on the velocity function, and here the stream function is varying based on the gradient of y. Here it is basically varying with respect to gradient of x. And here who cares? So these equations are said to be linear, and so what? Why we are doing this stream function and potential function study? Basically, we are doing superimposition of simple flows. That is, we have the complex flows, and we are having a simple flows and complex flows. The simple flows are nothing but the uniform flows and the streamline and the potential lines. And when you are trying to superimpose it, then it becomes as in complex flows. So via that, we are inventing the elementary flow models. Understand? So we can say, for an example, when you are worrying about the wing, how wing is generating the lift. So the wing is basically having the airfoil shape. So how this airfoil shape has been invented. So based on this, we have the faster and a simpler simplification of these elementary flow models helps us to make the clear-cut understanding in designing the wing. We need to understand some fundamental flows first. So what are they? See, we have uniform flow first. So the uniform flow is having the flow that is carrying under one direction. That is, we have x, y, and z direction in space. So when we talk about the 2D coordinates, so we have x axis and y axis. So with respect to x axis and y axis, we have the flow that has been maintained linearly with respect to x axis alone, is nothing but the uniform flow. So when the same uniform flow is operating at an angle of attack alpha, so during that time, what is the velocity potential equation and the stream function? So we are resolving the forces here, or we are resolving the x coordinate and y coordinate here. When you are resolving this x coordinate and y coordinate with respect to alpha, we have horizontal component and a vertical component. So the horizontal component has been classified here, and vertical components has been classified here. Next, we are going to discuss about source or sink flow. So previously we discussed about the uniform flow, but here the source flow that gives the clear-cut understanding in the radial flow. So we have the uniform flow that is said to be linear flow, and here this is said to be the radial flow. So at a single point where all the streamlines are coming out, and here in this we have the stream function and the potential function. So the potential function are in circular shape, but the stream function and the streamlines that are coming in radial form. And the velocity function and the stream function for this particular source or sink is formulated as phi is equal to strength of the source by 2 pi ln r, and then stream function as strength of the source by 2 pi into theta. So you know r theta, it is nothing but the polar coordinates. So with respect to polar coordinates, we are simplifying this, and then we have the velocity components. So velocity component, as you know how to derive it. So based on the derivation, we have the gradient function. So the gradient with respect to r, that gives Vr, and the gradient with respect to theta, that gives V theta. So this V theta is said to be 0. So it is nothing but the tangential velocity is 0, and here we have only the radial velocity as the streamlines are radial. Next, we are going to discuss about free vortex. So, what is meant by free vortex? Unlike source or sink flow, we have the free vortex where all the flows are spinning around the single point. So, what is spinning? So, here we have the center point that is spinning, where all the streamlines are spinning around. That is typically called as an vortex. And we have the center one, it is typically called as an core, where the strength of the vortex is maximum in the core. And then what happens to the vortex as radius increases? So the vortex strength decreases. And the velocity potential function here nothing but strength of the vortex by 2 pi theta. And then the stream function is given as minus of strength of the vortex by 2 pi upon, and we have ln r. When you make the derivation of velocity components, you obtain the radial velocity. See here we have the only the tangential velocity that is in circular form, so that we are having the tangential velocity v theta as strength of the circulation by 2 pi r. Next we have doublet. So about doublet with strength, that is nothing but ma by pi. Here what is meant by doublet? It is the source and the sink which are kept at an equal distance at a smallest distance, right? So when you are keeping the source and sink at a very nearest distance, so during that time the formation is typically called as an doublet. Via doublet, the circular cylinder is invented, and via doublet, rotating cylinder is also invented. And we have velocity potential flow, that is said to be pi is equal to k cos theta by r. Here k is nothing but the strength of the doublet, and k sin theta by r is nothing but the stream function. And when we resolve the velocity function, we have the radial velocity as well as the tangential velocity. Both the velocity has been superimposed. And when you add the source with a uniform flow, what happens? We obtain the Rankine Oval body. How this Rankine Oval body is obtained? See here we have the stagnation point here, and here we have the uniform flow. This uniform flow is coming and impacting on the stagnation point, where the source flow and the uniform flow meets together. When source flow and the uniform flow meets together, that point is a typical as stagnation point, and from this stagnation point all the flow velocities has been increasing, and then the stream function is given as pi bu, and the pi b is nothing but the depth of the Rankine Oval body, and b is nothing but the distance between the point of source to the stagnation point is typically called as an width of the Oval body, right? And here we have the flow around the Oval body, that is nothing but the velocity potential, that is pi is equal to ur cos theta plus m by 2 pi ln r, and then stream function as psi is equal to ur sin theta plus m by 2 pi theta, and the velocity components as radial velocity and then tangential velocity, which when you are going to derive this and we obtain the radial velocity and tangential velocity as two function, that is one is uniform flow as an which is nothing but the streamlines that are flowing around the doublet, and then we have the minus m by 2 pi r as an the object which we have the presence inside. So what if I add the sink to the mix? So when we have the source and the sink which has been mixed together, and when I am adding this to the uniform flow, what is the result? So let's see, the result is Rankine oval body. So how this oval body has been created? So we have the doublet, and we have the source and sink pair, and we have the uniform flow, and this source and sink is having the farthest distance. So it is not the nearest distance, it is the farthest distance, and from this farthest distance we have the uniform flow superimposition that leads to give the Rankine full body. So from this Rankine full body you find the two stagnation point, that is on the front as well as in the rear, and where we have plus m is nothing but the strength of the source and minus m as strength of the sink, and it is kept at a far distance. So we have the overall length of the Rankine oval body is L, that is 2L. And for this Rankine oval body, so we have the velocity potential function and stream function and body half length, that is nothing but the body half length, that is L value, that formulation, and body half width formulation. All the equations are here. So this has been derived as we have the summation of velocity potential function of uniform flow and a sourcing pair, like uniform flow, sourcing pair, all has been summed up, and body half length has been measured by measuring the velocity component, and you are making the velocity component to 0. So when you are equating the velocity component to 0, from that derived values, you are obtaining the value of body half length. So these are the parameters of Rankine oval body. Next, likewise, Rankine oval body, we have different types of bodies that will be discussed. So it is nothing but the airfoil. So how we are making the airfoil? So when we have the source and the sink pair, and when these are keeping at some point of distance, so unlike that, we have the formation of doublet, okay, and we have the uniform flow. So in the same preparation, when we are trying to increase this distance, that is when we are going to increase this distance, that is A and A, that is source and sink pair. So when you are adjusting this source and sink pair with respect to y axis or is a x axis variation, we will obtain the shape called airfoil. So about this we will discuss later on, and finally these are the topics we are going to discuss later, that is Bernoulli's equation and its application, and introduction to elementary flow models in airfoils, and then subsonic wing theory. Thank you.